we're going to take a look at our next unit in Chemistry 20 called Solutions, Acids, and Bases. And essentially this lesson is just to introduce you to the concept of solution, acid, and bases, and then we're going to dig more into each concept more as we progress through the unit. So to start out, a solution is a homogeneous mixture of at least one solute and one solvent. Now, a reminder that a solute is the entity that is being dissolved and the solvent is the dissolver. Okay, so it's the thing that causes, or it's the thing that dissolves, I guess, the solute. Now we have a variety of homogeneous mixtures that we can have, and they're listed below. We can have a gas in a gas, like oxygen dissolved in nitrogen. We have that in our air. We have gas dissolved in liquid. We have oxygen obviously dissolved in water. Okay, and this is in really important things like lakes and oceans, things like that, so that some of our aquatic life can live. Gas in a solid, oxygen in solid water, which we have in ice. Liquid in a liquid, which would be methanol or ethanol in water. Now methanol in water, we use that for antifreeze. Solid in a liquid would be sugar dissolved into water. We use that for syrups, things like that. And then a solid in a solid, we have tin dissolved in copper, which would be a bronze alloy. So some properties of aqueous solutions. We have these things called either electrolytes or non-electrolytes. And electrolytes are essentially compounds that in an aqueous solution, they conduct electricity. So let me just get my pen out here. Change this to a little cooler of a color. So they conduct electricity, meaning that they allow for the movement of electrons. That's super important as we go through. Now, electrolytes are compounds that conduct electricity, so non-electrolytes are compounds that when in an aqueous solution, do not conduct electricity. So do not conduct electricity. Okay, and we test this electrical conductivity with what we call an ohm meter. Now, electrolytes are also entities known as ionic compounds. Now, often when we hear the word electrolyte, we think of a sports drink that has lots of sugars in it and salts in it to help rejuvenate your body and hydrate your body. But electrolytes are a bit more than that. Okay, they're entities, again, that possess a charge and they allow for the movement of electrons. Now, electrolytes can be, let's see if I have this here. Oh, yeah. Okay, they're highly soluble ionic compounds, including acids and bases. So we have ionic compounds, acids, or bases that are all considered to be in this group of electrolytes. Now, if we look at non-electrolytes, generally they're molecular compounds, okay, and they form neutral solutions. So when I say neutral, the pH is equal to 7. Okay, so we have molecular compounds that form neutral solutions and they don't conduct electricity. So identifying solutions, there's a few things that we can do to help us identify certain solutions in a lab. So if we had a scenario where we had 3 or 4 different clear colorless solutions in our lab that we didn't know what they were, we could do a few diagnostic tests to figure out which is an acid, which is a base, which is a neutral substance, which is an electrolyte and a non-electrolyte. So we can do a bunch of tests to figure that out. Now, we know that if we have red litmus paper, now let me do this here. Red litmus paper So red litmus turns blue in a base, blue for base, and blue litmus turns red in acid. So we remember that our litmus paper can be a diagnostic test to figure out if we have an acid or a base. Now, generally when we test with litmus paper, we should always test both an acid and a base, or sorry, I should test with both my red and my blue litmus paper, because if red litmus paper stays red and blue litmus paper stays blue, then we have a neutral substance. We do not have a substance that's going to be either acidic or basic. So I want to be able to test with both. I should always test with both when I'm looking for a solution. Okay, another test that we can do is now this conductivity test. We know that ionic compounds, or acids or bases, will conduct electricity in a solution. So that's going to help us identify some of these solutions. So this is what we call qualitative analysis. This is qualitative. The reason that it's called qualitative analysis is we're looking at specific qualities of our entities given to determine what they are. So what I have listed is hydrobromic acid, sodium nitrate, lithium hydroxide, and methanol. So when I take a look at these, there's a few things that I'm looking for. I want to be able to identify a neutral solution. I want to be able to identify an acidic solution, a basic solution, and as well as my non-electrolyte or a molecular solution. So when I take a look at my first solution, solution number 1, I see that red litmus paper stayed red, blue litmus paper stayed blue. What that indicates to me is that this is a neutral solution. Okay, so this is neutral. Now, let's just jot that down. Now, the last thing I need to look for is I can have a neutral solution that conducts electricity that would just be an ionic compound dissolved in water, something like salt dissolved in water, sodium chloride. Now, in this case, I have my acid, which is hydrobromic acid. Lithium hydroxide is our base. I know it's a base because I have this hydroxide ion present. Sodium nitrate would be my ionic compound, and methanol would be my molecular compound. So when I take a look that there's no conductivity, I would say that this is our molecular compound. So I'm just going to put an M there for now, and we're going to go through the rest of this chart to see if there's any other glitches in figuring this out. So number 2, red litmus paper stays red, blue litmus paper turns red. So because we have blue litmus paper turning red, this is acidic. Okay, so I would guess that this is an A for acidic. Also, we expect acids to have high conductivity or some level of conductivity, and we do see that in our chart. The next one, we have red litmus paper that stays red, blue litmus paper that stays blue, and we have also high conductivity. This would indicate that we have a neutral substance, but because we have high conductivity, we expect it to be an ionic compound. Now we know that ionic compounds dissociate in water, so we know that this is going to break up into sodium and nitrate. Then we have our last example where red litmus paper turns blue, which means that this is basic, and blue litmus stays blue, and we have also high conductivity. We also know that bases ionize or dissociate in a solution, which we'll get to in a minute here. So when I go to label these, I see that my molecular compound dissolved in water is non-conductive, and it doesn't turn, it's neutral, it doesn't turn either of my litmus papers any color. So this would be my methanol. This next example we said was acidic, which would be my hydrobromic acid, or HBr. My third solution is neutral, but it has high conductivity. So this would be our sodium nitrate. Also neutral, but high conductivity. And then our base is at the bottom, and we know that our base is lithium hydroxide, or LiOH, lithium hydroxide. So we can do this qualitative analysis to determine a variety of substances if we're unsure. And these are called diagnostic tests by doing litmus paper or a conductivity test. Those are diagnostic tests that we can use in the lab. Now, there's two words that come up in this unit, and one is called dissociation and one is called ionization. Now, they are essentially the same thing because they are both talking about a compound breaking into ions. Now, with dissociation, essentially dissociation is for the separation of ions when an ionic compound or base dissolves in water. Where ionization is a process where a neutral atom, so almost like a molecular compound, is converted to an ion in solution. Now, the one thing I want you to keep in mind is that in general, we talk about ionization where we have an ion being formed from a molecular compound. However, what we know now about a lot of our compounds that do undergo ionization is that they include hydrogen ions as an entity. Now, when this term ionization was derived, we didn't really fully understand the properties of hydrogen, and now we know that hydrogen has both metallic and non-metallic properties. So when we're talking about ionization, we're talking about the breaking up of something like hydrochloric acid, which I'll demonstrate in a minute here. But we actually know that hydrogen now exhibits very metallic properties, so we have an ionization formula for that, but essentially it is identical to a dissociation equation. So let's take a look at an example. If we look at ionization, if I give you the example of sodium hydroxide, which is both an ionic compound and it's a base, we would get sodium and hydroxide ions. And that's essentially all that we do for a dissociation equation. Okay, if I look at something more complex, I could look at calcium, let's do calcium phosphate. This dissociates into calcium, 2 positive, and I have 3 of them. I can't forget how many I have. And I have 2 phosphates. So these are my dissociation equations. Now with ionization, again, we start with a neutral atom, and I'll give my example of my hydrochloric acid. And HCl ionizes into H positive and Cl minus. And those are the examples that we see where we often, like I mentioned, have hydrogen in our compound or molecule that gets converted into an ion. So these terms are sometimes used interchangeably. However, we do still prefer to use the word dissociation when it comes to ionic compounds or bases, and ionization generally with our acidic compounds that have a molecular compound that is separated into its ions. So, what are charged particles called? Well, just a reminder, they're called ions. We either have cations with a positive charge, and I remember that because the T looks like a positive, or we have anions. And this is just the way that I have always remembered it, that I can write out the word anions with all negative symbols. So because of that, I remember that the cations are positive, anions are negative. So in a solution, electrolytes dissociate. So we have something like sodium chloride, and in water, we get, so in water we say aqueous, we get sodium and chlorine ions. Where with non-electrolytes, we just spread our neutral particles. So if I have something like glucose or sugar that's dissolved in water, I just get individual sugar molecules. But this whole sugar molecule, because it's neutral, okay, it's a non-electrolyte, this entity will just spread individual molecules around. So this will not break up or dissociate in any manner. It will just, the smallest form that it will break into is an individual glucose molecule. So we see that we have electrolytes that dissociate, and because of this dissociation, you'll notice we get this charge, okay, on our ions. So we have Na positive, which means that this sodium lost an electron. And who did it lose it to? Well, it gave it to this chlorine right here. It lost it to this chlorine. So because of that, I get Na positive and Cl minus. But notice that because there is a movement of electrons, this is why electrolyte solutions can conduct electricity. That is super important. Now, you might remember our pH scale. Oh, just one thing to go back, sorry, before I get too crazy here. Anytime that we have a solution that is our solvent is water, if we have, say, this term right here that I have NaClAq, this AQ means it's dissolved in water. If I have Al, it means that it would be dissolved in alcohol. So AQ is water as our solvent. And if I have Al, it means alcohol is our solvent. Now, generally, we would use something like ethanol as the solvent in that case. Now, back to our pH scale. Sorry that this image is a little bit blurry. I'm not sure what happened here, but you should all be pretty familiar with the pH scale. It is a concept that we've touched on throughout your schooling career. So essentially, I want to just take a look and remind you that our really, really acidic entities are entities with a very, very low pH or pH less than 7. And our basic entities are entities that have a pH of greater than 7. And notice that right in the middle is our neutral entities, okay, which is a pH of 7. So water is neutral, something like that's acidic, like hydrochloric acid is very low pH, and something like a drain cleaner or sodium hydroxide has a very high pH. Now, essentially, when we talk about acids and bases, there was this man named Arrhenius that basically came up with our sort of definitions of what an acid and a base is. So when he described bases, he described them as ionic compounds that were hydroxides. Okay, they dissociate into a positive ion and a negative hydroxide ion. So if we look at this example, I have barium and I have hydroxide, and this should be balanced. I have 2 hydroxides. So it breaks up into 2 entities, one being the cation and one being this negative hydroxide ion. So he said anything that dissociated to immediately form this hydroxide ion was basic. Okay, and we have this dissociation. Now he also said that acids, since they're electrolytes, because they conduct electricity, they must have some sort of ions present. They ionize, notice the difference in terminology here, they ionize into a positive hydrogen ion and a negative ion when dissolved in water. So again, we have our example with hydrochloric acid dissolving into hydrogen ions and chloride ions. Again, we see this ionization of our 2 ions, hydrogen ions and chloride ions, and we see that this would be an electrolyte because we do have this ionization. And again, this hydrogen ions being formed is what makes something acidic according to Arrhenius' theory. Now, if we look at sort of the empirical definition, now this is what we see in the labs, and this is the theory behind what we see. We see that acids turn blue litmus red and are electrolytes, so that's something that we've talked about. And another property of acids is that they neutralize bases. Okay, neutralize if you have a really low pH and you have a really high pH. Neutralizing means that you bring them to a pH of about 7. So we see that with acids. And Arrhenius' theory said some hydrogen compounds ionize to produce hydrogen ions, and hydrogen ions react with hydroxide ions to produce water. So a neutralization reaction would be hydrogen ions with hydroxide ions. Now, bases are basically the inverse of acids. They turn red litmus blue. They are still electrolytes. We see that they neutralize acids, which is exactly the opposite of what acids do. And they are ionic hydroxides and they dissociate. Now, notice our 2 different words. We have ionize and we have dissociate to produce hydroxide ions. And the hydroxide ions react with hydrogen ions to produce water or a neutral substance. Now, neutral substances, when we talk about them, okay, we're talking about generally a solution. They do not affect litmus paper, so they do not have a color change on litmus paper. Some are electrolytes, like ionic compounds. Some are non-electrolytes, like molecular compounds. Okay, no hydrogen or hydroxide ions are formed, and some are ions in solution. These are our electrolytes, and some are molecules in solutions, which is our non-electrolytes. Now, when we talk about solutions and dissolving entities in water or any other solvent, we often need to refer to some energy changes. Now, with an endothermic, endo and exo are your sort of key words to look for when we're talking about this. Endothermic reactions absorb energy from the environment, where exothermic reactions release energy to the environment. So we have these two different principles that we have to consider when we're making solutions. Now, depending on what we're forming, it will depend on if we have an endothermic or an exothermic reaction. And now often, when we dissolve either a strong acid or a strong base in a solution, we result in a highly exothermic reaction. Now, depending, like I said, on what we're doing, it might change whether we have an endothermic or exothermic reaction. Now, one thing we need to talk about is that generally, if we break bonds, breaking bonds requires energy. We need to have some sort of energy input to break those bonds. And forming bonds, in general, releases energy. So by forming bonds, we have energy produced. Now, when we're talking about dissolving entities in solution, there's a few things that happen. Sometimes we both break bonds and form bonds in this dissolving process. So if we look at an example of dissolving sodium chloride, we see that dissolving NaCl will use energy to form our sodium ions and our chloride ions. When we dissolve that, we have the breaking of the bonds between our sodium and our chloride, and we break ionic bonds. Okay, we also break some intermolecular forces between water molecules because we're dissolving in water. We're adding water to this to dissolve. And because we know from our last unit that water has a variety of intermolecular forces, in fact it has London dispersion, dipole-dipole, and hydrogen bonding, that when water interacts with the sodium chloride, it essentially has a polar side, or a polarity, that the negative side will attract to the positive ions of the sodium, and the positive side will attract to the negative ions of the chlorine. So we actually sort of break apart some of those intermolecular forces between our water molecules. Now, in that process, energy is absorbed, or used. But when we see that we have sodium and chloride ions produced, well, then there's a new electrostatic reaction or force between those ions and the water molecules, like I mentioned. So we have the positive ions attracting to the polar negative side of our water molecule and vice versa for our negative ions. And in that reaction, energy is released. So when we have a certain amount of energy absorbed, that net energy change is the energy absorbed subtracted from the energy released. So we have whatever our net energy changes is a result of both of these reactions. And depending on what we feel, if it's either exothermic, if it's exothermic, then we've had bonds that have been formed. And if it's exothermic, the bonds formed outweigh the bonds broken. So if it's endothermic, it's the opposite. If it's endothermic, the energy absorbed to break those bonds is greater than the energy released from new bonds being formed. So we need to consider that as we go through and understand that when we do have the creation of certain acids and bases, especially when we dissolve them in solution, we can get an endo or exothermic reaction. Now, like I said, if we make a very strong acid, we're going to have more towards an exothermic reaction, same with if you were to dissolve a strong base in water. Now, because we have very exothermic reactions, just a hint for when you're in the lab, which I call the A and W rule. because it's very important that when you're diluting an acid or a base, or when you're creating an acid or a base, so if you're dissolving maybe some sort of acid in water or base in water, you always want to add the strong acid to the water. The acid, you don't want to add the water to the acid. It's not the W and A rule, it's the A and W rule. Now, I like A and W because, I mean, it's a restaurant chain, right? But I like to remember A and W because if you add the acid to the water gradually, you will get a more controlled exothermic reaction. If you're to add water to acid, you can occasionally cause some, depending on the strength of your acid, you can cause some spattering due to the exothermic reaction, which can be very dangerous. You can spread some acid either on yourself or your surroundings, and also which can cause both chemical burn as an acid burn, or it can cause heat burn too, because it is an exothermic reaction. So you always want to add your acid to your water, and I call it the A and W rule. So that's just a thing to note as we talk about these energy changes. Same thing goes for the bases, but the B and W rule doesn't quite sound as cool as the A and W rule. So with our energy changes, the dissolving process is either endothermic because more energy is absorbed than released, or exothermic because more energy is released than absorbed, which I kind of alluded to at the end of that last slide there. Now, substances in water. Now, because we are talking about solutions, we really need to remember our solubility charts. Now, I do believe that you probably would have gone over this in your Science 10 course, but if you haven't, we're going to take a look at our solubility charts in the next couple lessons here, but you do need to be pretty familiar with these charts. Okay, now, acids and bases must be dissolved in water to have any sort of reaction. So this is why we're talking about substances in water and our solutions, acids and bases. So acids that are good conductors are called strong acids, which we'll talk about a little bit later. This is due to the degree of ionization. And weak acids don't ionize as well as strong acids do. Now, another thing to be very, very aware of, and you might have remembered this from our previous unit on our first unit on chemical bonding, but we have polar and nonpolar substances, and this is depending on the net dipole in a substance. So polar substances generally dissolve polar entities. So if we have water will dissolve, because water is a polar entity, water will dissolve other polar entities. So if we have a nonpolar substance, we have it to dissolve nonpolar entities. So what you might find is that something that's nonpolar can be like an oil or a wax, or sometimes it's those really sticky gummy tape that you get left behind on your labels on any of your dishware or water bottles or whatever, and they're really gummy, yucky substances. Now, what you might find is that when you use water to take that off, unless the water is really screaming hot, that doesn't really do a great job. However, because it is more towards the nonpolar entity, if you're to take like a vegetable oil or an olive oil or coconut oil or whatever and rub off any sort of sticky label, you'll actually find that that works significantly better to remove a sticky label rather than water, because you're using a non-polar substance to dissolve a polar entity. So that's pretty cool to talk about as we go through. Now, this is super duper important. This is why if you were to try and dissolve olive oil in water, it won't happen. You're going to have separation of your oil and water. Okay, that's because oil is non-polar and water is polar. If you were to try and dissolve coconut oil in olive oil, you would have some success because you're using a non-polar entity to dissolve another non-polar entity. So that's important as we move forward as well. Again, this polarity should be fresh in your minds from our first unit that we talked about in Chemistry 20. And as you move forward, it's good to have all of these concepts of electrolytes, non-electrolytes, conductivity, and pH in the back of your mind as we move forward in this unit, just to be sure that you are understanding all the concepts. And these are the ground floor building blocks that we really need to be certain on prior to moving forward into any other concept in this unit. So, good luck!